Have you ever stopped to think about what's really holding molecules together? We learn about these neat little sticks connecting atoms, but the real story is, well, it's a whole lot weirder and more fascinating. It's a quantum story. Today, we're going to pull back the curtain on chemical bonding with a really powerful idea: molecular orbital theory.
But first, let's start with a genuine mystery. We all know oxygen, right? The gas we're breathing this very second. But if you get it super cold, so cold that it turns into a liquid, something completely bizarre happens. Liquid oxygen is magnetic. I mean, it will literally stick to a powerful magnet. How is that even possible?
And here's where it gets really strange. Our normal way of thinking about chemical bonds, a model called valence bond theory, predicts that oxygen should have all of its electrons neatly paired up. And if that were true, it would be diamagnetic, which is just a fancy way of saying not magnetic at all. But experiments show us, plain as day, that it's paramagnetic. It's drawn to magnets. So what we see in the real world directly contradicts our best theory. That's a huge puzzle. To get to the bottom of this, we have to go deeper. We need to bring in the big guns, an advanced framework that looks at bonding in a totally new light. And that tool is molecular orbital theory, or MOT for short. It's basically designed to explain all the weird stuff that the simpler models just can't touch. So what's the big idea here? Well, get this. MOT says that when atoms come together to form a molecule, their individual atomic orbitals, they don't just hang around. They actually cease to exist. They're totally replaced by a brand new set of molecular orbitals that belong to the entire molecule, not just to one atom or the other. It's like melting down two separate Lego creations to build one bigger, completely new one. So how does this happen? You have to remember that in the quantum world, electrons act like waves. And when these electron waves from different atoms get close, they interfere with each other, just like ripples spreading out in a pond. And this interference can happen in two really important ways. First up, you can get constructive interference. This is when the waves line up and add together, reinforcing each other. This creates a really stable, lower energy orbital called a bonding molecular orbital. This is the good stuff. This is the quantum glue that really holds the molecule together. But you can also get the exact opposite: destructive interference. This is when the waves are out of sync and they cancel each other out. This creates a high-energy, totally unstable orbital called an antibonding molecular orbital. This one actually works against the bond. It's actively trying to push the atoms apart. And this is the key difference right here. Every time two atomic orbitals combine, you get this pair. One bonding orbital that's lower in energy and makes the molecule more stable, and one antibonding orbital that's higher in energy and makes it less stable. It's this cosmic tug of war, and the balance between them decides whether a stable molecule can even form in the first place. Okay, so we have these new bonding and antibonding orbitals, but where do they all go? How do we organize them from lowest energy to highest? Well, it turns out there isn't just one single layout. It's a little more complicated than that. The arrangement actually depends on this really subtle but super important effect called sp mixing. It's basically an interaction between the s and p orbitals that can shift their energy levels around. And depending on whether this mixing happens or not, we get two different blueprints for our molecular orbital diagrams. And here's how that breaks down. For smaller molecules, think nitrogen, and anything with 14 or fewer electrons, sp mixing is a big deal. It actually pushes the energy of the sigma bonding orbitals up above the pi bonding orbitals. But for larger molecules, like our mystery guest oxygen, there's no sp mixing, so the order is different. The sigma orbital stays at a lower energy level. This little switch is everything. So why the split? It all comes down to the energy gap between the two s and two p atomic orbitals. In those smaller atoms, the gap is pretty small, so they can easily interact or mix. But as you move across the periodic table to oxygen, the nucleus gets more powerful, it pulls that 2s orbital way down, and suddenly the energy gap is just too big for them to mix. All right, we have all the pieces now. We have our theory, we have our two blueprints. It's time to finally go back to that first question and solve the mystery of magnetic oxygen once and for all. First things first, let's count the electrons. A single oxygen atom has 8 electrons, so an O2 molecule has a grand total of 16. And since 16 is obviously greater than 14, we know exactly which blueprint to pull out, the one without sp mixing. Now we just have to fill that diagram up with our 16 electrons. And we just follow the same basic rules you'd use for filling up orbitals in an atom. You start at the very bottom, at the lowest energy level, you put 2 electrons in each orbital with opposite spins, And this is the important part. When you get to orbitals that have the same energy, you put one electron in each before you even think about pairing them up. That's Hund's rule. So let's do it. We start filling up the diagram for O2. The first 14 electrons fill up all the lower orbitals, nice and neat. But what about the last two? Well, they land in two separate antibonding orbitals that have the exact same energy. And because of Hund's rule, they stay separate. They don't pair up. And bam, this leaves us with two unpaired electrons. And that's it. That's the answer. It's a fundamental fact of physics that unpaired electrons act like tiny little magnets. Because the O2 molecule has two of them, the whole molecule generates a weak magnetic field. And that's why oxygen is paramagnetic. Mystery solved. I mean, how cool is that? This is the true power of molecular orbital theory. It brilliantly explains a basic property of one of the most common molecules on our planet, a property that simpler theories just get completely wrong. It gives us a much more accurate picture of how the world actually works. Oh, but wait, there's more. This diagram gives us another incredibly useful piece of info, something called the bond order. The calculation is really simple. You just take the number of electrons in all those stable bonding orbitals, that's 10 for oxygen, and subtract the number of electrons in the unstable antibonding orbitals, which is 6. You take that difference and divide it by 2, and you get a bond order of 2. That perfectly matches the double bond we've always drawn for oxygen. And bond order is a super useful number. It basically tells you the net number of bonds holding two atoms together. If the bond order is greater than 0, you've got a stable molecule. And the higher the number, the stronger and shorter that bond is going to be. So let's just recap the big takeaways here. Molecular orbital theory isn't just some abstract idea, it's a predictive powerhouse. It gives us a far more accurate picture of what chemical bonding is really all about. It explains properties like magnetism that are complete mysteries to other models, and it gives us awesome tools like bond order to predict whether a molecule is even stable. You know, it really makes you think. By looking at a simple molecule through this new quantum lens, we uncovered a secret property that was hiding in plain sight the whole time. It leaves you with this amazing question. If MOT can do this for oxygen, what other incredible secrets of the molecular world are out there, just waiting for us to unlock?